Welcome! Today we will explain how to solve a specific type of second-order ordinary differential equation. So let's get started with the definition of a second-order ODE. First thing here is that we will deal with second-order linear ODEs. So remember the definition of linear from the previous lecture. That means that the derivatives of the function and the function itself appear in a linear form in the differential equation. And here we deal with second order ODEs, so the higher order derivative that appears is second. So that means that the coefficient related to y prime prime must be different from 0. Because this term must be there in order to have a second order linear ODE. Okay? Now, today we will solve a very specific type of second order linear ODE. We will add some adjectives. And the first one is that today we will only deal with homogeneous type of second order linear ODE. So that means that f of t that appears in the right hand side, so everything that does not depend on y, it's in the right hand side, yeah? So we are assuming today that f of t is equal to 0. That means that the equation is homogeneous, okay? So let me point here that we are dealing with linear, homogeneous ODEs, and we will add another adjective. We will only deal today with constant coefficients. Now, what's the meaning of that? You can see that the coefficients that were multiplying y prime prime, y prime, and y here were dependent on t. Okay, they could depend on t. When we say that we only deal with constant coefficients, that means that now the coefficients a2, a1, and a0 that multiply the function, the first derivative and the second derivative, they are real numbers, okay? So they do not depend on t. They are real values. 3, 2, square root of 2, whatever, but they are real numbers. So today, we will only deal with a lot of adjectives, yeah? Second order, linear, homogeneous, with constant coefficients, ODEs. Okay, let's see how we can solve this very specific type of ODE that we can write in this manner, which we can write in this manner, okay? This is a second order, constant coefficients, linear, and non-homogeneous. Today, we will deal with the homogeneous, as I said, so we will skip this remark here. We already explained that, and we will go now to the theorem. Now, this theorem says that given the specific type of differential equation I want to solve today, which is homogeneous, second order, linear, and with constant coefficients, okay, we have the 4 adjectives, then the general solution of this very specific type of differential equation is very easy to be found. It's just a linear combination of 2 linearly independent particular solutions. So what's the meaning of this theorem? If I'm capable to find 2 different particular solutions of this differential equation I want to solve, then the general solution is very easy to be written. It's just the linear combination of these 2 guys. So the problem of finding the general solution now is simplified to just finding 2 particular solutions. Any particular solution you can find. It doesn't matter if it's the easiest one. I don't care. I just need two of them. Okay? This theorem is very easy to be proved. You have just to substitute yt in the ODE and you can verify it satisfies the ODE, so it's the solution, and it's the general solution because it's a second order ODE and it depends on two constants, C1 and C2, that can be any real value one. Maybe we could have written this here. Okay? So today we will just use this theorem to solve this specific, very specific type of ODEs. Okay? So what we need to do is just to find two particular solutions, y1 and y2, particular solutions of this ODE, and we are done. We can write down the general solution. So let's go for it. What we want to do is that we want to find two particular solutions, and we will start trying with the exponential functions. We will see in a few seconds why is this a very good choice, and it's because of the linearity and because of the constant coefficients that we have in our ODE. Okay? So I will write down here our ODE. It is y prime prime t plus a coefficient that will be constant times y prime t plus a0 yt equals 0. This is the specific type of ODE we will solve today. As you can see, I have a 1 here because I can always divide the whole equation if I have another value different from 1 here. I can just divide all the equation by that number. So I can just always rewrite it in this way. So the coefficient that multiplies y prime prime is a 1. Then it's very important that a0 and a1 are just real numbers. Okay, now we propose to check if this could be a particular solution of this very specific type of ODE. Let's try. Yt is proposed to be the exponential. Let's compute the derivative of the exponential. Well, it's just itself, but I need to multiply by the derivative of the exponent, which is s. And then I need to compute the second derivative. Now again, this s here is just like constant because we are taking the derivative with respect to t. So this s just remains there. Now I will compute the derivative of the exponential, which is again itself, but multiplied by the derivative of the exponent with respect to t, so that's s. So I get s squared here. So I think it's clear that y is the exponential, y prime is s times the exponential, and y prime prime is s squared times the exponential. And now we will just substitute these y prime and y prime prime into the differential equation that we want to check if y is solution. That's what we do here. Y prime prime, okay, is this term here, and is written here, okay. This term is y prime prime t. Okay, let's continue. Now, plus a1 y prime, okay. So this is plus a1, and this is going to be y prime. You can check that y prime is s times the exponential as we written here. We continue. Now plus a0 times y, so plus a0 times y, so this is y. So what we did is just to substitute y prime and y prime prime into the differential equation. And what we did here in the right hand side is just to take the exponential as common factor here, yeah. Then what remains inside the parentheses is s squared plus a1 times s plus a0. Oh, wait, that looks a lot like the ODE. It has a lot of similarity with the ODE. Yeah, instead of s squared, I have y prime prime. Instead of s, I have y prime. Instead of 1, I have y. Okay, but it has a similarity. We'll see this is helpful in the future to solve this type of ODEs. Now I will just continue. Now, I know that this should be 0. Okay, because the equation is telling me that this should be 0 if y is a solution. Now, what do I know about the exponential function? Well, what I know about the exponential function is that it's never 0. It never crosses the x-axis, the exponential function. So I know that this guy is never going to be 0. So for sure, this term here must be the 1 being 0 if the product is equal to 0. So this means that this equation is the one that should be 0. So I summarize what we got here. If we want this yt that we propose to be the exponential of st, if we want this to be solution of the ODE, we need s to satisfy this equation. So that way this equation is going to be very important. It's going to be called the characteristic equation. Now, in order to find a solution, a particular solution of my ODE, it's going to be as simple as solving a second-degree equation. This characteristic equation. Wow, that's really easy. So, what we concluded now is this. The exponential of st is a particular solution of the ODE I'm interested in. When s is obtained solving the characteristic equation, which is this equation we saw here. Now, what can happen with the second order equation like this one? Yeah, I'm sure you are more comfortable maybe thinking in this type of equation. Yeah, something like this. This is a parabola, you know that, and you can plot it using, for example, the x-axis. And if I ask you, how many solutions can this parabola have? How many times can it cross the x-axis? Well, I'm sure that in this case, it's very clear to you that it can happen that it doesn't cross the x-axis at all. Maybe it will not cross, but touch the x-axis once, or maybe I will have a parabola that will cross the x-axis twice. So we know that this second-degree equation can have 1, 2, or no solution at all in the real numbers. So that will depend on what? Well, everybody knows by heart, I think, this formula. I'm just applying the formula everybody knows to solve second-degree equations. And of course, the fact that this has 1, 2, or no solution in the real numbers depends on what happens inside the square root. If the square root is 0, you only have one solution. If the square root is different from 0 and is positive, then you have 2 different solutions. But if what's inside the root is negative, then you have 2 solutions in the complex numbers, but no solution in the real numbers. So, to proceed now, we really need to separate or to take into account three different cases. Case 1 is the easiest one. We are very lucky, and we got 2 different real roots, S1, S2, that live in the real numbers. That would be this case, yeah? And we are very happy because with that, we have 2 different particular solutions to use and solve the ODE and get the general solution. Remember that our purpose was to find 2 different particular solutions. That's what we got here. The second case, case 2, is when we have what's inside the square root is 0. So what we get is that we have equal real roots. In fact, S1 and S2 are equal. So we are in this case where we are just touching the x-axis once. So in this case, okay, we got one particular solution for this particular value of s that we got, but we need another solution, another particular solution in order to really solve the ODE and get the general solution. So we are not done here. We need to work a little bit more. And case 3, normally when we are a little not that comfortable because we need to work a little bit with complex numbers. We get here 2 different solutions, but they live in the complex numbers, and we need to work a little bit more here in order to get 2 solutions in the real numbers, because that's what we are trying to do. So first thing here is to summarize what we said. We have that 3 different cases depending on the value of what's inside the square root. We can call this value that is inside the square root the discriminant. Here we use nabla letter to call it. And basically for case 1 we are done. And what I will do is to show you an example for this specific case that we already solved the equation. So for example, let's say I have this ODE. First thing I need to do is a checklist. Is it second order? Yes, because the maximum, the derivative of higher order that appears is second order. So it's a second order ODE. Great. Is it linear? Well, yes, it is linear because y prime prime, y prime, and y, they appear linearly in the ODE. Okay, they are not just in a square root or with a power of 3 or multiply between them or inside an exponential and so on. Okay, now what else? Is it, does it has constant coefficients? Constant coefficients? Yes, because the coefficients are 1, 3, and 10. Okay, so they are real numbers, they are constant. And finally, is it homogeneous? Well, yes, that's very easy to check. The right-hand side is equal to 0. So we can try to solve it using what we explained today. And that is that for this specific type of ODE, we know that the general solution is given by the linear combination. So C1 and C2 could be a real number, where these Y1 and Y2 are particular solutions, okay? So the only thing we need to do to solve this ODE is to find 2 particular solutions. And we know, because we checked before, that when we try particular solutions that look like this, they verify the ODE if S, that appears here, satisfies the so-called characteristic equation. This is the characteristic equation, okay? Now, the first thing I need to do is to solve the characteristic equation. Now, the characteristic equation is always s squared in the place of y prime prime plus 3s in the place of y prime and minus 10 times, and I will write just the 1 in the place of yt and equal to 0. So this is the characteristic equation. I will solve it very easily. Everybody knows by heart this formula. Very important that you do not commit any error here. It is simple, but don't commit, calculation errors. In this case, we get that inside the square root, I have 49, so I can compute the square root. And basically, I have 2 different cases. When I use the plus sign here, 7 minus 3 is 4, divided 2 is 2, I get this value. When I use the minus sign, then I have minus 10 divided by 2, which leads me to this second equation here. So we found two different real numbers as possible values of s. So we found that the exponential of 2t is one particular solution, and the exponential of minus 5t is another particular solution, linearly independent to the other one. They are different solutions. So the general solution of the ODE, that's what we were looking for, is just the linear combination of these two solutions, particular solutions we got, okay? Remember here that C1 and C2 are any real numbers you want. So this is when the characteristic equation has two real and different solutions, and that is when we call this case 1, okay? And that's what we explained before, that for this specific case, case 1, we already know what to do because we got two different solutions, and that's it. Now, we need to work a little bit more for the other two cases. Let's start with case 2 now. Here in the slides, you have another example. You can try to do it yourself, okay? You can pause the video and try to do it yourself and check you can do it correctly. Now, the second case, case 2, this is when we solve the characteristic equation, and it happens that what is inside the root is 0. So, of course, we get only one solution for this second order equation. So we need another solution because this is only one particular solution and I need two of them. So what we will do is we will try with this type of particular solution, which is just the exponential we had before, but multiplied by t. Let's check if trying with this type of solution, we can prove it is a particular solution of the ODE. In case it is clear that it's independent of this one that we tried before. So in case we can really check it is solution, then we are done because we will have two different particular solutions and we can write finally the general one, okay? So here what we are doing is just checking if y2 is proposed to be this formula, then we can compute y prime 2, just following the multiplication formula to take the derivative here. So the derivative of t is 1 times the exponential plus t times the derivative of the exponential, which is itself times s. And then we need to compute the second derivative. So we will just do the calculations and we will get that is this formula here. Now we will use these formulas of y prime, and yt, and we will plug them into the ODE. Remember that our ODE is this one. Okay, so we need to plug in this equation these formulas here, and this is what we do in the next slide. Okay, this is y prime, this is y prime, this is y, and we are substituting them into the ODE we are trying to solve today. Okay, once we substitute it into the differential equation, we decide to take common factor t exponential of st and also to take as common factor the exponential of st. And we can see that for this case, t exponential of st, I have this term, a0, that appears here. Then I have a1 times s, that appears here. And I also have s squared, that appears here. And then I will change color. For this term, the exponential of st, I have this term 2s times the exponential, and the other one remaining is a1 times the exponential of st. All the other terms have already been used, okay? Okay, now let me clear this. And what we can see here is that we know that this is 0 because this is the characteristic equation. Characteristic equation. So as S is solution of the characteristic equation, this must be 0. And we also know that this is 0. How do we know that? Well, because, let me go back once. We know that for our case 2, means that the discriminant is 0, what is inside of the square root is 0. So that gives me that the value of S is minus a1 divided 2. So that's the value of S. Minus a1 divided by 2. I know that a1 is I know that S is minus a1 divided by 2. So this 2 simplifies here, and I get minus a1 plus a1, and that is 0. So we verified that when I plug into the ODE the y2 I proposed, the result is 0. So it verifies the ODE. So we can ensure that this is a particular solution of the ODE. So this case 2 now is already solved. We have two linearly independent particular solutions. The first one is just the exponential. The second one is t times the exponential. I will use always the same value of s, okay? The only difference is that t multiplying here. And the general solution of the ODE is just the linear combination of these two solutions. So this is case 2. Let's see an example. Let's suppose I want to solve this ODE here. First thing always is to check our list of adjectives. Is it second order? Do I really see and understand that it's second order? Yes, that's very simple. The highest derivative is the second derivative. Okay, is it linear? Do I really understand what's the meaning of linear? Do I really see it's linear? Y prime, and y prime prime, they appear linearly in the ODE. They are not multiplied between them into square roots or inside an exponential or sinus functions or whatever. Okay, it's linear, we see that. Does it has constant coefficients? We really understand the meaning of this? Well, yes. The coefficients that multiply y prime prime, y prime, and y are constant because they are real numbers, 1, minus 10, and 25. Okay, so I'm verifying all this. And finally, is it homogeneous? Well, that's very simple. I can say that is equal to 0. Okay, so it verifies all this. I know that I can solve it just finding two particular solutions, and the general solution is going to be the linear combination of these two particular solutions. And in order to find these two particular solutions, I will first start trying to solve the characteristic equation. In this case, when I solve the characteristic equation, which is this one, I hope everybody understands how the characteristic equation is written from the ODE. I think it's quite simple. S squared comes from y prime prime, minus time s from minus time y prime, and the 25 from the coefficient that multiplies y. I need to solve this equal to 0, and in this case, it happens that what's inside the square root is equal to 0. So I only get one solution, and this is case 2, remember. Case 2 means that, in fact, I don't get two different solutions, but only one. I will call it S, okay, which in this case is 5. And I need another particular solution because I only got one of them. I got only this one. Remember that we are proposing as solution the exponential of st. We are finding S, solving the characteristic equation. That's one solution, but I need another one. Well, we did in the previous slide the work to check that in general it's going to be true that just multiplying by t will be another particular solution. So, in fact, we have now two different particular solutions, the exponential and t times the exponential of 5t. So just doing a linear combination of them, we get the general solution of the ODE. So that's for case 2. Again, you have another example here. You can pause the video here and try to solve it yourself and see you really understand. And we go now to the last case, which is case 3. Now, in case 3, we are very lucky because in fact, we obtain two different solutions. The only small problem we have is that they are complex, and we would like to have it in the real numbers, okay? So let me show you here what's going on in this case. What's going on here is that what's inside the square root is negative. So I decided to write it here in this way. I will call this nabla letter, and I know it's going to be negative in this case. That's why I get complex numbers. And the nicest way to write the solutions of the second degree equation here is to use, of course, the convention that I is the imaginary unit, okay? So that's why I'm writing here minus nabla, because now minus nabla is a positive number, yeah? And I'm just taking outside here I, which is the square root of minus 1. So at the end, what I get is two conjugate roots, which look like this, okay? Alpha is the real part of the complex number, and beta is the imaginary part of the complex number. So in this case, in fact, we have two different solutions. One when using plus here, and another solution when using a minus here. But we don't want to give the solution in the complex numbers. So we would like to work a little bit in order to give the solution in the real numbers. And in order to do that, it will help a lot this very simple theorem. And the theorem says the following. If I have a solution in the complex numbers, so if it's a solution in the complex numbers, it has a real part and it has an imaginary part, then it can be proven that if this is a solution of the second order ODE that we are working today, okay, linear, constant coefficients, and homogeneous, then also the real part by itself and the imaginary part by itself, they are both particular solutions of the ODE. Okay, so what I said is that if I have a complex solution of my ODE, I can use the real part as one particular solution and the imaginary part as another particular solution of my ODE, because both are solutions of the ODE. This is very easy to be proven. You know, it's very difficult to solve an ODE, or it can be very difficult, but it is very simple to verify if a function is solution. It's as simple as substituting into the ODE. That's what we are going to do to prove it. Now, I have my ODE, the ODE we are working today with, which is this one, okay? And I want to prove that if this is solution, then U and V are also solutions. Okay, so what I'm going to do is plug into the equation this YT. I know that yt is solution. Okay, so when I plug it into the ODE, it verifies the ODE. So who is y prime prime? Y prime prime is just take the second derivative here and the second derivative here. Who is y prime? Y prime is just computing the first derivative here and the first derivative here. And y is just, I will just copy the definition of y. Okay. Now, I know that this is equal to 0 because yt is solution of the ODE. But now I want to check whether u and v are also solutions. So I will rearrange terms. I will put everything that depends on u here and everything that depends on v here, which happens also to separate what's the real part of the number and the imaginary part. Remember that the imaginary part is everything that multiplies I, the imaginary unit. Now we know that this is equal to 0. Well, 0 in the complex numbers could be also written like this. 0 plus I times 0. Yeah, so it has a 0 real part and a 0 imaginary part. So if what we have written in the left-hand side is 0, that means that the real part must be 0. And that means that the imaginary part must be 0. So that's what proves that u is also a solution of the ODE. Because look, this is the ODE. You can see that this is exactly the ODE we are trying to solve. The only difference between this and the ODE I want to solve is that instead of y, I'm using here u. This is exactly the same ODE. A1, A0, A1, A0. U prime, U prime prime. I prime, I prime prime. So u, when plugged into the differential equation, gives 0. So it's a particular solution. And the same happens here for v. What I have here is the ODE written using v. And I know this is equal to 0. So v is another particular solution of the ODE. So in summary, we got complex solutions like this one. We are going to use the plus case because it's easier. Remember that we had a plus and a minus solutions. I'm just going to use the one with the plus because just using one complex solution, I will find two different real solutions. How? Splitting the real part and the imaginary part. How we can do that? Well, from this expression that we have of our solution, I will write the real part, the imaginary part. I will use the very well-known Euler's formula to rewrite this part here in this manner. I suppose you remember this from Calculus 1, okay? And now I can separate the real part, which is this one here, and the imaginary part, which will be the exponential with the sinus. Now, the previous theorem showed that the real part is a solution, is a particular solution, but also the imaginary part is a particular solution. So finally, we have two independent particular solutions, and we can write down the general solution of our ODE, which is just the linear combination of these two particular solutions we got here. Remember to write always that these C1 and C2 are any real numbers you want. And let's see a numeric example of this third case. Let's say we want to solve this ODE. Of course, we must check that this second order. Yes, we must check it is linear. Yes, you must also check it has constant coefficients, which is true. I have 1, -6, and 34. And finally, today is very important that is homogeneous, which it is, because it's equal to 0. Now, first thing we will do is solve the characteristic equation, which is this one here. I hope now everybody understands very easily how to write it. And when I try to solve it, it happens that what I have inside the root is negative, -100. So I can write this in this manner. I is the imaginary unit, square root of -1. So I got here two complex conjugate roots. And I'm going to use only this one, okay? Because just using one complex solution, I will be able to find two real solutions. Remember that in this case, this is alpha and this is beta that we had in the previous slide. Remember that this is giving me the real part of the complex solution, and this is giving the imaginary part of the complex number. So in this case, alpha is equal to 3 and beta is equal to 5. So yt, maybe the first time I will write this as the linear combination of y1, which is in this particular case e to the 3t times cosinus of 5t, plus c2, this is y1, plus c2 y2, which is the exponential of 3t times the sinus of 5t, and now this is y2, which of course we can rewrite by taking the exponential of 3t common factor and write it in this manner that we have here in the slide, okay? So this is what I wanted to cover today. You have one more slide with another extra exercise you can try to do yourself to check you really understood how to solve it for this third case I have shown. That's it for today. See you in the next lecture. Bye bye.